About a disorder that is near and dear to my heart, Aicardi-Goutières syndrome. And my goal is really just to do the general scaffolding so that you can kind of gather the information from the talks that are going to follow. So I will give the initial overview, and then we'll have Francesco Gavazzi of our group at the Children's Hospital of Philadelphia join in on outcome measures. And finally, it's our pleasure having Dr. Markus Hofer coming in to talk about mouse models of AGS. We had a very robust work group meeting and more people that have asked to join after the fact. So please reach out to me if you would like to weigh in on AGS. So I want to thank everyone who participated in our group beforehand. I want to talk briefly about AGS because it is uniquely complicated in that it is a monogenic disorder, but there are at least 9 different genes that are associated with AGS, 2 of which are new since our last GLIA meeting pre-pandemic. And so it is, in general, a disorder of immune dysregulation. And there are both endo and exonucleases, such as TREX1 and RNase H2, A, B, and C, as well as RNA tagging and sensing machinery, like IFI-H1 and ADAR1. And then the 2 new genes are actually involved in histone modification. And so these all play together to result in immune dysregulation and activation of the immune system through the type 1 interferon pathway. Because AGS is actually an autoimmune disease that we have co-opted into neurology because it does affect brain development so much, it actually is a systemic disorder. And so like another disorder I'll be talking on later today, MSD or multiple sulfatase deficiency, one of the challenges is that it affects everything, but it doesn't affect everything in every child. And so figuring out outcome measures and ways to measure something across a diverse disease that affects everyone slightly differently, I think is a barrier that we're grappling with now. We have many successes to tout. The AGSAA is our wonderful patient advocacy group, and they have mobilized an IRB-approved patient registry. They're mobilizing families around the world to join together to facilitate research. We have a broad phenotypic spectrum, which I'm not going to talk about much because Francesco is going to be touching on that. And we're beginning to gain a deeper mechanistic understanding so we can start to develop more targeted therapies to help children with AGS, and Dr. Hofer is going to talk on our preclinical models. As far as biomarkers go, we've been using both neotrin and tetrahydrobiopterin from the CSF for decades, and we've also been using in the laboratory basis something called an interferon signaling score, or gene expression score, which indirectly measures the way of how much the interferon pathway is stimulated. But it's probably more complicated than that, and we're working on developing and validating additional biomarkers to help us to better understand why some kids are more severe than others. There have been several clinical trials in AGS, although none have been placebo-controlled. There is a small pilot study using reverse transcriptase inhibitors, and our own study using Janus kinase inhibitors demonstrated in post-hoc analysis an improvement in overall neurologic trajectories. But I think one of our biggest challenges in AGS is this really broad phenotype that we see and a limited known genotype-phenotype correlation. When you look at sibling pairs, some of our most affected siblings, their older sibling is one of our mildest kids in our cohort. And so how do we better understand the other factors, environmental, diet, infectious, other polymorphisms and immune genes that are influencing that degree of severity? And I think it becomes really important, too, as we're starting to counsel families and saying, you need monitoring in every single organ system, always, please. And it's just an infeasible task for families. And if I can better understand, if you made it to 3 and you don't have thyroid dysfunction, then we probably only need to screen as needed. And things like that to really limit that burden of healthcare of our children of AGS is going to be huge. We've done some preliminary work where we have looked at 191 subjects that are enrolled in our GLIA CTN natural history study, along with 125 published case reports, to begin to pull out who has each complication of AGS and at what age do they come on. So things like seizures and glaucoma are associated with AGS when it begins in the first 6 months of life, so that early onset ultra severe disease. whereas things like skin inflammation and hypothyroidism don't appear to be as dependent on early onset. And so there are additional factors, such as probably genotype, that we will begin to parse out. I love this quote from Patrick Winters. I don't know if he's here today. I haven't seen him yet. Oh, hi, Patrick. A prognosis does more than guide clinical interventions. It determines how a family views and frames their lives. And so our ability to predict the future is helpful for us in designing clinical trials, but it's essential for families as they're starting to frame their lives. And so I think it's an ethical and moral imperative. We can help guide families better than we do now. And there are also no FDA-approved therapies. There is the published Janus kinase inhibitor, and some families are receiving this off-label, but it would be groundbreaking and really help families if we can get an FDA-approved therapy. Our Heatmap has delightfully changed in all the right directions, but it's still nowhere where we need it to be. And so, whereas before we had a lot of reds and dark oranges, we now have a lot of greens, meaning we're moving in the right direction really across the board in AGS, but we're nowhere near where we need to be ultimately. So with that, I'd like to invite Francesco to talk about some of our successes in AGS and outcome measures. So thank you.
Good morning, everyone. So today I will try to give you a snapshot on one of the many projects that we're working currently to understand which are the possible outcome measures that we can use to evaluate efficacy of any kind of treatment in rare disorders, including AGS. So first of all, clinical outcome assessments are quite polyhedric in the way that they can be administered, because they can be patient-reported outcomes or caregiver-reported outcomes, but they can be also clinician-reported outcomes, so something that the clinician observe and score in a specific moment, but it's more collected by history that parents tell. Observed reported outcomes like quality of life, skills, and then performance outcomes. So assessments that are performed in a specific moment in time and are observed or administered by a provider. And these are the ones that tend to be more performance sensitive on the specific period in time in which they are administered. Because as we're starting to learn more and more, multiple rare conditions, and specifically for AGS, the performance between one day and the other can change quite dramatically. So it's important to take in consideration that variability and trying to pair it with something that is a little bit more predictable and average of a performance. Another element that we need always to take in consideration when selecting outcome measures is to have a clear idea of what is the population that we are trying to describe and what are the goals of our evaluation, because there are a lot of possible areas of evaluation of outcome measures. Motor assessments, and we can divide them into gross motor and fine motor, but also psychomotor development or cognitive abilities later on in life. Adaptive behavior abilities, so how the child is able to actually adapt themselves to the requirements of the environment and in general, the different domains of life, and quality of life, which to some extent summarize the previous ones. And we need to take in consideration that ideally we want to find something in which the population that we're going to explore is not going to perform at a floor effect, so the test is so difficult that we're not able to discriminate between different groups of population performance, because everybody tends to score on the lower register of the test, but also something that on the opposite is not too easy. So trying to avoid biasing the selection of a measure towards the population that tend to be more affected by a condition or less affected by a condition. And so we always need to find that sweet spot in between. How do we validate outcome measures in rare disorders? That's something that is very relevant, because the selection of outcome measures should always be followed by administration of them to try to see if the performance in the population is valid, and at the same time, if there is like a meaningful selection of those from a methodological and scientific perspective. And so once the outcome measure is identified as a possible one for administration, we usually need to go through a process of phase validity, particularly for situations in which there is nothing yet published in literature around this. And then the phase validity process is a very simple one. So it's based on a selection of a measure, and then a group of people that tend to be more expert on the disease than expert on the measure vote with a Likert scale. Do I like it? Do I don't like it? Do I think it's appropriate? Do I think it's not appropriate? And then we administer the measure at predetermined time intervals to see, first of all, if the measure performed well in a one shot, but also if the measure is sensitive to change over time, and if it's sensitive to the dynamicity of the disease. And then we need to perform analysis to evaluate floor and ceiling effect, appropriateness, and possible identification of key items for a shorten up of the assessment. I just mentioned about the phase validity process. I wanted to mention that this is quite accepted methodology at this point. It's been published for more than 30 years and almost 40. And it seems to be quite the to-go approach in these rare disorders that don't have yet published data. I will now present you some of the work that we're doing on AGS on evaluation of performance of outcome measures in the population, and I'm going to focus the talk on gross motor assessments, and specifically what is the performance of the population at a widely administered assessment for gross motor performance that is a gold standard, and it's used in multiple clinical trials as sort of an outcome measure, the GMFM-88. It's an assessment that is comprised of 88 items, and it was originally developed to evaluate motor function and efficacy of intervention in children with cerebral palsy, so with children that have a condition that is supposed to be stable over time. And there are 5 dimensions that are increasingly more difficult. And so we evaluate the ability of a child to have floor mobility and head control up to more complicated gross motor abilities such as walking, running, and jumping. And it's a test that it's supposed to evaluate a pediatric population, but it can be adapted and expanded for later ages as well, and it's expressed in a percentage. And I want to mention that ideally this test was created to have the majority of the population be as close as possible to 100%. We enrolled 71 patients in this study, and we had also some longitudinal data on these 71 patients, even though I'm going to present only the first assessment for every patient, so sort of a cross-sectional analysis. And in the population, the age at disease onset was quite early, as expected for AGS, so 0.55 years with a median of 0.25, but a range that was quite varied. So we go from disease onset at birth up to 3 years of age. And the age at the evaluation was quite distant from the age of onset. So the median was about 4 years and the mean actually 6 years. So we need to take that in consideration, that we are evaluating a population that tend to have had quite a long experience with since disease onset. And so we can see that the performance, it's quite varied. So about 2/3 of the cohort tend to perform below 20% the GMFM-88, which we framed as sort of a floor effect. There is no clear way methodologically and statistically to define a floor effect in a test that is not like standardized scores and percentiles, but that's our cutoff. But you can see that there are quite a few situations in which the performance tend to be way above this level. And some of the dimensions don't suffer floor effect, specifically dimension A, so what concern more the floor mobility and the head control. And once we try to divide the population and see if there is a performance and a correlation genotype-phenotype, we see that there is quite a spread in the performance in a lot of genotype, with maybe the exception of TREX1, in which the majority of the population tend to be a bit more severe. But you can see how for SEMHD1 the spread of performance is quite varied. And then we paired these GMFM88 scores, percentage scores, with the AGS severity scale. That is a scale that was created specifically for AGS to discriminate the severity levels between the different patients. And it's an assessment that tends to be a little bit more granular in the low functional population. So you can see the spread by genotype. And we were able to show that, with the exception of TREX1, in which the floor effect performance is quite strong, there is quite a good correlation between the performance at the GMFM88 and the AGS severity scale for all the different genotypes. And so this is quite reassuring in the sense that we're able to determine that the GMFM88 has a possible role in its use in AGS, maybe with some modification of it. So ideally, we would like to try to be a little bit more comprehensive in the lower range of functionality in AGS. Particularly, we are seeing that the AGS, the GMFM88 tend to be useful and tend to have a role in a population that has an AGS score above or equal to 3, so what we consider moderate to high functioning AGS. And maybe we can try to find creative ways to try to address both to try to understand how to better describe the lower performance in AGS, but also to see if this assessment is also valid to show the dynamicity that characterize AGS. Maybe trying to understand specific correlation with decline in the GMFM88 and a possible decline in the AGS score, and so to see if it's able to capture both improvements and pitfalls of performance. And I would like to thank all the people that are collaborating in this project. This is definitely a group effort, and particularly when it comes to outcome measures, it takes a village to try to understand as much as possible about these. And so I would like to thank Laura, Adeline, our amazing statistician, our amazing therapist that are really, really knowledgeable about all the tools that we're using and are able to help us in trying to understand better ways to refine them for our use, and in general, all the people that are supporting our work and this amazing group that I have the luck to be part of. And thank you so much.
And next, we'll have Dr. Hofer come and speak to us. Thank you.
Good. Thank you very much. So the next 15 minutes, I try to give a short overview of mouse models for Aicardi-Goutières syndrome and the perspective that we've gained from them, but also a lot of the open questions that still need to be addressed using mouse models and other preclinical models. Just to very briefly recapitulate the steps that lead to the clinical disease Aicardi-Goutières syndrome. We've got at the very beginning genetic mutations. At the moment, there's 9 genes that have been identified where mutations are causative for these diseases. They typically lead to the abnormal accumulation and processing of nucleic acids. This then in turn triggers an inflammatory process resulting in the chronic production of interferon alpha, primarily in the central nervous system and to a much lesser extent in peripheral organs. And this then is thought in turn to drive the neurodegenerative and neuroinflammatory disease we see in patients. Now, in Aicardi-Goutières syndrome, we're actually quite fortunate. There's a large number of different mouse models. The last time I counted, there's somewhere between 15 and different genetically modified mice that all try to address this disease and the mechanisms that lead to that disorder. Now, interestingly, the vast majority of these mouse models focus on the genetic mutations we see in patients. And they either do that by trying to mimic these genetic mutations or by knocking out these genes completely in the mice. And these mouse models really have been invaluable in providing clarification how specific gene mutations lead to exaggerated interferon alpha production. I'm just going to highlight that for two examples, that is Trex1 and ADA1. So Trex1 is a cytoplasmic 3' exit nuclease whose physiological role it is to degrade double-stranded DNA. So normally, double-stranded DNA should be secluded to the nucleus and the mitochondria. However, even under physiological conditions, small amounts of double-stranded DNA can leak into the cytoplasm where they are then degraded. Now in patients, but also in mouse models where we have a reduced activity of Trex1 or absent activity of Trex1, this double-stranded DNA accumulates in the cytoplasm where it's then recognized by the nucleic acid sensor cGAS, and then cGAS binds to STING and triggers a signaling cascade resulting in the activation of the transcription factor IF3, which then drives the chronic production of interferon alpha. And what I've shown here is basically the summary of a large number of different studies over the last 20-odd years, and I've just here listed a few of these studies, and by any means this list is not complete, so I apologize to anybody who's here whom I haven't named on this list. Now ADA1, in some ways a very similar story, but in some ways also quite a different pathogenetic process that leads to the disease. So ADA1 is a nucleic acid modifying enzyme. It recognized specifically so-called zRNA. zRNA is a conformation of double-stranded RNA, which is highly immunogenic, and ADA1 detoxifies this highly immunogenic zRNA into a more immunotolerant version. Now, in the absence or reduced activity again of ADA1, this nucleic acid zRNA is recognized by nucleic acid sensor, in this case MDA5, which then through MAFs activates IR3, and we get the same chronic induction of interferon alpha production in cells. Now, more recently, another zRNA binding protein, ZBP1, has been identified. ZBP1 also contributes to that inflammatory process. The exact molecular mechanisms by which it stimulates that MDA5-mediated production of interferon alpha is still uncertain. But in addition, more recently studies have shown that ZBP1 can also directly induce cell death, in particular necroptosis, which is a pro-inflammatory form of programmed cell death, and therefore contributes to the disease. And again, this has been done in large numbers of studies. As you can see in the bottom, actually, a lot of these findings were not published until last year and this year. Now, while these mouse models, these genetic mouse models have provided good clarification on how mutations lead to interferon alpha production, none of these mouse models really truly recapitulates the pathological and clinical features we see in patients with AGS. Okay, that's a limitation of all of these mouse models. Now, in addition to these mouse models which recapitulate the genetic mutations, there's also one existing mouse model which tries to recapitulate the agnostic common effector pathway in AGS, that is the chronic production of interferon alpha in the brain. Now, these mouse models, which have been now around for about 25 years, originally developed by Ian Campbell at the Scripps Institute, also called the given mice, which is short for GFAP interferon alpha transgenic mice, and these mice chronically express interferon alpha 1 in astrocyte under the control of the GFAP promoter. And unlike the other mouse models, these given mice actually recapitulate both the clinical and the pathological features we see in patients. I've just summarized that here on the slide. For example, the mice develop calcifications in the medial ventral forebrain, as shown here on the micro-CT image. They also have calcifications in the cerebellum. This is an alizarin red stain. We see neurodegeneration, we see inflammation and myelin degeneration in these mice, and a widespread white matter disease. Now, we have been using these mice over the last few years trying to understand which cells in the brain actually mediate the disease that we observe. And we started out doing this by performing single-cell RNA sequencing, here for brain cells from wild-type mice and interferon transgenic given mice. And if we focus here first on the schematic here in the middle, it's a Heatmap plot and dimension reduction approach. We can see that we can cluster the cells based on the transcriptomes. For example, we've got in green the astrocytes, in 13 microglia, and in 1 vascular endothelial cells. Now we then separated these cells into cells originating from wild-type mice versus the transgenic mice in blue versus orange respectively. And there's 2 observations we can take from that. The one is that for most cell types, these cell identities overlap, indicating high degree of transcriptional similarity between these cell types. For example, for astrocytes shown here on the top. However, 2 cell populations stick out which separate when we divide up by genotypes. These are the endothelial cells and to a lesser extent the microglia. And this indicates rather pronounced differences in the transcriptomes of these cell types. Now we are particularly interested in the endothelial cells. The blood or the vasculature within the brain in patients with Aicardi-Goutières syndrome and also in this mouse model really hasn't been considered very much over the last few decades. So we decide, okay, let's have a closer look at them. Do these mice actually develop a sort of microangiopathy? And to summarize a large number of experiments, the answer is yes, they actually do develop a rather pronounced microangiopathy that is characterized by the activation of the blood vessels, perivascular immune cell infiltrations, calcifications that are associated with the blood vessels, and rather strikingly, very prominent microaneurysm formation in these mice. So we went back to the patient's tissue. We obtained patient tissue from the NIH Biobank, from patients with AGS and from some other collaborators, and we find the same microangiopathic changes in the patient tissues. We've got the perivascular immune cell infiltrations, the calcifications, which are very prominently associated with the blood vessels, and here shown an angiogram, these microaneurysm in formation in at least a subset of the patients. Now, we then asked the question, are these microvascular changes just a pathological feature, or actually do they contribute to the disease process? And in order to address the question, we had to generate a new mouse line, a new triple transgenic mouse line, which we call the GIT mice. And these GIT mice overexpress interferon alpha in the brain, as do the given mice, but the endothelial cells in these mice are no longer able to respond to it. We knocked out the type 1 interferon receptor specifically on endothelial cells using an Krelok's approach. Now, if you first look at the microvasculature in the different mouse lines, if you compare the given mice with the wild-type mice, the given mice have this microangiopathy with these enlarged vessels that I just mentioned and the microaneurysms, and this is completely restored in the triple transgenic mice, indicating that endothelial cell-specific inactivation of type 1 interferon signaling is sufficient to prevent this microangiopathy. Does it also have a functional consequence in these mice? And we were particularly interested in the integrity of the blood-brain barrier. And to test that, we injected peripherally dyes into the mice, Evans blue and fluorescein. As you can see here, for the given mice, the dyes accumulate in the brain, indicating a massive breakdown of the blood-brain barrier. And again, this is restored in the triple transgenic mice. Now, we then went on and asked, does it also protect from other features of the neuroinflammatory neurodegenerative disease? We performed a large number of studies, and again, summarizing that here on a single figure slide. Doing histology here, particularly of the cerebellum, this is the area of the highest transgene expression in the given mice and in the GIT mice. And you can see here in the given mice, we've got these calcifications, primarily in the cranial cell layer. We've got an angiopathy with these enlarged blood vessels, this white matter disease, and also a rather prominent microangiopathy. And again, these features are absent in the triple transgenic mice, demonstrating that endothelial cell unresponsiveness to interferon alpha is sufficient to protect these mice from these disease changes. Now, does it actually have clinical consequence? Because ultimately we want to help patients. And again, I only have time to summarize here in one slide. So we performed a number of behavioral tests. This one here is a rotor rod test, which measures motor coordination. These mice develop pronounced ataxia. And you can see in red here for the given mice, these perform significantly worse compared with the wild-type mice, whereas the triple transgenic mice perform intermediate between the wild-type mice and the given mice. Now, this is also reflected on the survival time. These interferon transgenic mice start dying from about 4 to 6 weeks of age. By 32 weeks, the end of our observation period, less than 20% of the mice are alive. And by contrast, in the GIT mice, they have a significant longer survival with roughly 70 to 75% overall survival at 32 weeks of age. So what we think happens in these mice, in the case of the disease process and potentially also in Aicardi-Goutières syndrome patients, we've got initially this response of the brain's vasculature to the chronic interferon alpha production. This leads to transcriptomic changes, particularly changes in the expression of cell adhesion molecules, inflammation-associated molecules, and chemokines. This triggers then a microangiopathy with microaneurysm formation, perivascular calcification, and critically also a disruption of the blood-brain barrier, allowing the leakage of neurotoxic molecules into the brain. It also supports the transmigration of immune cells into the brain parenchyma and contributes to gliosis and neuronal cell death. So what I've tried to really briefly here give an overview that mouse models have been really critical in illuminating both the molecular but also the cellular pathogenesis of Aicardi-Goutières syndrome. They've also shown that pathogenetically, at least, AGS is not a single disease, but is a rather heterogeneous disease with multiple molecular mechanisms that drive interferon alpha production, including accumulation of nucleic acids, necroptosis, but all the differences or changes in histone composition more recently. And the findings in the given mice, which we've done and performed in recent years, show that microangiopathy might be a major contributor to disease in Aicardi-Goutières syndrome. And that's important because it obviously allows to develop new therapeutical strategies which more specifically target this brain vasculature. Finally, I have to acknowledge the people who performed the experiments, and particularly Barney Biancu here, as a PhD student, now a postdoc in the lab, and our funding partners and collaborators both in Australia and overseas. Thank you.
So much. I don't know this is on, but thank you so much. I'll now ask our work group leaders to come and have a seat. And we have time for a couple questions. Are they working? I think so. This one's not. Hello? Oh.
Thank you. Okay. I usually don't need a microphone. Francesco, I want to come back to something that Laura opened up with, which is the contribution of environment and diet and stress. When you did the GMFM 88, which let me just say, 88 is a lot. I probably couldn't have gotten through it myself. Did you take that into consideration with those results? Because I'm sure that must impact how well they can do.
So we took in consideration some variables. We didn't take in consideration specifically diet. So we took in consideration age of onset. We took in consideration length of disease. We took in consideration genotypes. So apparently chronological age was not associated with a specific performance, and age of onset was only loosely associated with the performance. So it's pretty clear that there is something else that will probably need to be investigated from like a specific pathogenetic evolution of the disease, because and we were also seeing the fact that, as Laura mentioned, siblings, some of the siblings that we have that share the exact same mutation, sometimes they also have a closer age of onset one to the other, tend to perform dramatically differently. So probably is that. Another element that probably we'll need to take in consideration is to see into a more geographically international cohort, so maybe including some patients from other continents to see if there are also some other like genetic backgrounds that can modify a little bit this approach, because probably by increasing the cohort, we also can have a sense of what is the spread. Because as we've seen before, like the performance varies dramatically, and is not only for the gross motor, we're also doing other assessments for evaluating fine motor, cognitive, adaptive behavior abilities. We're going to roll over soon, like quality of life assessments. So probably we'll need to define more than a specific motor profile, more of a performance profile and functionality profiles that might be a little bit more able to guarantee and to evaluate differences, and also taking in consideration other variables now that we're starting to see that genotype is not enough, age of onset is not enough.
Francesco, we're going to take two questions over here, and then I saw one more question there, and I think that might be all we have time for.
Yes, I have a question about the interferon alpha overexpressing mouse. Do you think that the microangiopathy is an endothelial cell autonomous phenomenon?
I don't think it's necessarily autonomous to the endothelial cells. Parasites, which we also knock out the type 1 interferon receptor using our TEC-CRE approach, likely contribute to that disease.
Yeah, because theoretically, if you look at the pathogenesis of calcification in the blood vessels in the CNS and microaneurysm formation, you need to involve the tunica media. So you need to involve the smooth muscle cells and the pericytes, depending on the vascular.
Yeah, we haven't yet gone down to a parasite-specific knockout, but that's on our list to do, yeah.
Okay, thank you.
I think this is really wonderful work. I actually had a very similar question, but unless there's a new Tie2-CRE on the market, I think it also definitely targets the parasites. But also, we've seen some microglia recombination in targeting some of the primitive macrophages. Have you done transplant in your model?
No, we haven't done transplants in the model. We know that in our TEC2 approach, we do not knock it out in microglia. So we confirmed that the microglia still have a functional type 1 interferon receptor and signal.
Thank you. For Francesco, for the endpoint GMFM 88, and I remember you got 71 subjects and 250 measurements. So I assume there are some subjects have more than one measurements. Have you plotted the trajectory of those points and to see, because if you use that as for clinical trials, we may want to see change from baseline. So even though the natural history study data will be different from the placebo arm, just want to see how this endpoint change with age.
Can you repeat the question? This microphone doesn't work.
Yes, so basically I was asked because of the subsequent number of administration that we've done on the GMFM88 on a single patient, if we started to plot the trajectories of patients to see basically how they are doing over time. And it's going to be the next step of our analysis. There are some challenges associated with it, specifically the fact that now we are evaluating patients into a more precise and recurrent and predictable interval between one administration and the other. Unfortunately, the COVID-19 pandemic disrupted quite a lot the regular administration of these assessments, and we were able to validate a remote administration of the GMFM88. So now we're going to be able to do a better job in being more regular in the evaluation of patients. Also, there are some other elements, like some patients started evaluations of the GMFM88, but then had some treatment administered, specifically baricitinib. So we'll need to take in consideration those changes, but it's something that we're going to do in the future to see if the GMFM88 is able to be used as a longitudinal tool, or maybe a variation of the GMFM88 might be better to describe this population over time. But we're going through that.
I have a question also to the mouse work. When you compare, I mean, this really nice that you knocked out the receptor in endothelial cells. It's cool work, really. But did you compare this to knocking out the receptor in microglia and see then to evaluate which is the contribution of the signaling pathway for the disease?
We are working on that. We have done that. Preliminary results indicate that microglia deficiency does not have a significant impact on the mice on the overall survival.
Okay.
Pathological changes, it has some impact on it, but we have a relatively small number of mice at this point.
Thank you.
It's quite surprising, yes.
Sorry, we have literally 1 minute left, so go ahead.
Okay, say for the transgenic interferon transgenic mice in the brain, expression in the brain is not a surprise cause the brain degeneration and inflammation. And how much the transgenic mice mimic the patient, the level, expression level of in the brain of your the mouse is comparable to the human, and also you knock out the receptor is only partially rescue the animal. So that means besides the interferon pathway, your model means something else independent of the interferon alpha. You agree that?
Yeah, trying to address the question. Practically, it's still very difficult to measure interferon alpha level in mouse brains. None of the ELISAs that we have tested work. If you compare the interferon score as an indirect measurement, okay, we see changes between wild type and given mice that are comparable to those you would see in patients with AGS. So we've done that together with David Hunt in Edinburgh. So in that sense, the levels are comparable, at least from the functional aspect downstream. The second part is, yes, we do have active interferon signaling in the brains of these mice, which is not surprising because the triple transgenic mice still produce the same amount of transgene as the given mice. And apart from the endothelial cells, all of the other cells of the brain still respond to it. So microglia, astrocytes, neuronal cells, etc. So I'm not surprised. Actually, I would be more surprised, if not shocked, if these mice were cured, okay? I probably think something would have been wrong if the mice would have been cured. The interferon responses just in neuronal cells itself is sufficient, I would assume, to cause an effect on these mice.
All right, thank you very much for that robust discussion, and thank you very much to...
I just wanted to quickly introduce two of the patient advocacy representatives from the AGSAA. We have Patrick Winters and Devin Cordova here. Is there anyone else from AGSAA that I'm missing? All right, so for Adeline's button challenge, they're the two that you need to come and talk to.
All right, thank you very much.